sequence. Okay, so now, first thing you need to know is for an infinite geometric sequence, your ratio has to be between -1 and 1. That means that basically, all that means is that it's a fraction. Okay? So as you can see, my t to the 1 in this case is 8, right? My common ratio, what am I multiplying by to get from the first term to the next term? 1/2. So that falls into our range here of -1 to 1. Now, if I look at the sums of this infinite geometric sequence, so I'll start with 1. So 8, and then S2 is 12, S3 is 14, S4 is 15. I'm just going to extend this now. Okay, so S5 then is 15.5. S6 then is 15.75. Oh, that's not 15, that's 12. 15.75. And then S to the 7 would be 15.125. Come on, Jared. 875. Okay? So, as you're looking at the sums of this, what do you notice about the sums as we're going through here? Make a couple observations that you can make with the sums.
They're increasing by half as much each time.
Okay, there's one. What else can you tell me about the sums? What do you notice?
There's a pattern, but I can't explain it.
Okay. Well, we know that each time you put a term down, it's half the previous term, so we're increasing by that. But just take a look at the numbers. We started at 8, right? And then we went in about 3 terms, we went to 15, right? And then what happened? Then we started to go up by smaller increments. No? Right, so we got to 15, now we went up by 15 and a half, 15.75, 15.875. Okay, so they're going up slowly now. So what's going to happen here is there may be a number that they're going to come closer to, but not hit. Right? This is going to keep going infinitely, forever. But the sum is going to have somewhat of a peak moment. Like it's going to come close to a number, but not actually get there. So this is how we find the sum of an infinite geometric sequence. The infinity sign you've seen when we do the ratios. Oops. So the sum of an infinite geometric sequence is t to the 1 over 1 minus r. Yeah.
Is it going up, because 8, 12 is going up by 4, and then 2, and then 1, and then 0.5.
Yeah, it's the same, it follows this pattern right here. Right? So I'm adding on all of these. So as those get smaller, this goes up by a smaller amount. Okay? So with an infinite geometric series or sequence, you're going to have a max value that it's going to approach but never actually get to. So to calculate that, my t to the 1 is 8 over 1 subtract a half. 8 over 1/2 is 16. So this infinite geometric series is going to continue to get larger and larger and larger and closer to 16, but it's never actually going to get there. Now this can only happen if my common ratio falls between -1 and 1. Meaning that it's a decimal or a fraction. So I'm multiplying to get to the next term by making the next term smaller. Okay? Any questions about this? So far?
So what happens if it doesn't fit?
If it's outside of this,
Yes.
then we say it's diverging. Okay, so there's the other thing. Sorry, I should have stated that. A converging geometric series is when it approaches a value. So that is when your R is between -1 and 1. That's a converging one. A diverging means that your sequence is going to go forever, your series is going to go forever, but it's never actually going to have an end point. So an example, so this is when your R is greater than both of those. So either your R is, how do I want to write it, greater than 1, or R is less than -1. Okay, notice there's no equals to because you can't have a ratio of 1. So this is what we call diverging. So an example of that would be this: 2, 4, 8, 16, and so on. So if you look at the sum, first term is 2, second term is 4, so your sum is 6, and your sum is 14, your sum is 30. It keeps going forever. So it means that it's diverging. And it's important that we know this because there is a question that you'll be asked about whether or not a sequence is diverging or converging. Okay? All right?
So you can't ever find the sum of a diverging.
You can get the sum if you know the nth term, if you know which term it is, but it's going to go forever.
Right.
Whereas this guy is going to have a max value that it's going to come closer to but not actually hit. Okay? So let's take a look at your first examples there. Decide whether the infinite geometric series is convergent or divergent. The sum of the series, and then find the sum of the series if it does exist. So 0.5 to -1 plus 2 minus 4. So all that you need to do is find your common ratio to begin with. So what's your common ratio in that question?
Negative.
Yeah.
-2. So is it converging or diverging? Diverging. So there is no sum of it. What about the next one?
1/4.
1/4. So that has a diverging one, right? So let's find out. What was the first term? 12 over 1 minus 1/4, which is 12 over 3/4, which is 12 times 4 over 3, which is equal to 16. Okay? You can fill in your blanks as you go there, if you'd like.
Which question?
42. You're welcome. So far, so good? Any questions?
So the first one is convergent.
Converging, no, first one's diverging.
Okay.
Diverging means, okay, so let me explain this a little bit better. So converging means comes towards something. Okay? So you're coming towards something. Diverging means you separate, or you go away
Okay.
from. Okay? That's the easiest way to explain that, I think. All right. Let's look at page 43. Let's look at our example. First month, an oil well in Manitoba produced 36,000 barrels of crude oil. Every month after that, it produced 95% of the previous month's production. Write this series in terms that represent the situation. Okay, so term one. Term one. What is the, how many barrels did they produce in the first one?
36,000.
36,000. I want to find term two, but in order to find term two, I need to know my common ratio. What's my common ratio?
0.95.
0.95. Okay. So, take 36,000 times it by 0.95. What do we get? $34,200. And then let's find term 3. Perfect. Okay, so all I'm doing is taking each term and multiplying it by 0.95 to get the next term, correct? Yeah? Okay. So far, that's all right? So, it says, if this trend continues, what will be the lifetime production of this well? So, this is an infinite geometric series, right? Because the ratio falls between -1 and 1. So, I need to know then, is there a maximum amount of oil going to make that's going to be produced?
Mm-hmm.
There is. It's going to be, eventually the oil is going to run dry. Okay? So here's what I'm going to do. S1, or term 1, sorry, 36,000 over 1 minus 0.95, which is 36,000 over 0.05.
Need a big number though.
Should get a large number, yeah.
720.
720,000? Right on the nose?
Well,
That's the total production of its lifetime.
okay, so like T21 smaller than T1. That's just all.
Right. So now I'm adding up all the barrels until the barrels go empty. Right? Until we get to, I mean, in theory though, we would consider it being empty, but it would keep going because you'd just be taking out less and less and less and less. You'd have partial barrels at that point. But so the total number of barrels that would be almost max would be about 720,000 barrels. Okay? What assumption are you making about the well and its production? Is your assumption reasonable? Any assumptions?
It'll run dry. I don't know.
Yeah, it'll run dry, for sure. Okay. We are going to look at working example 3. This is the confusing part of the entire section. So far we've done arithmetic sequences, arithmetic series. We've done geometric sequence, we've done geometric series. We're doing infinite. Now what we're going to do is a part that's going to be slightly confusing to you. This again is what I kind of pointed out to you at the start of last week when we got into this course. It's just, can you follow the steps in order to solve the question? In this case, this is very structured, very step-oriented. It says, apply the sum of an infinite geometric series to express the repeating decimal 2.135 repeat as a fraction. Okay, so we want to change this. We want to change that into a fraction. Okay, so now we understand that a repeated number is a rational number, meaning that it should be able to put it into a fraction. Okay, 1/3, for example, decimal 3 repeat, 2/3, right? 0.6 repeat. Okay, so we should be able to put this into a fraction form. So we're going to use our infinite geometric series, okay, equation in order to change this to a fraction. So the first thing I do is I separate out 2.1. All right, and I'm going to focus just on the 35 right now. Okay? Now, I want you to watch what happens here. So this is your tens, hundreds, thousands. So that becomes 35 over 1,000. All right? Now, if I just simply get rid of the line for a second, and I put another 35 here, I'm going to have 35 over 1,000, 10,000, 100,000. Okay, so far? How many zeros did I add on?
2.
2? Okay. One more time. Add 2 more zeros. Like that. So far, so good? Okay. Is there a value, if I'm looking at this in terms of a sequence, geometric sequence, is there a ratio that I can multiply this by to get to there, and then this to get to there? And if so, what is it? What is it? How do I multiply, what do I multiply 1,000 by to get to 100,000? Was it? 100. So I am going to multiply by 1 over 100. Anybody not follow that step? So far I'm looking at this, it says t to the 1 is, if we're just focusing on that, is 35 over 1,000. R is 1 over 100. The series is convergent because it's minus 1 is less than R is less than 1. So put those in. Follow through on your book. This is a good one just to follow the steps. So what is my T1 value? 35 over 1,000. So that goes into that box. So infinite geometric. 35 over 1,000 over 1 subtract 1 over 100. Okay, so just set them into your boxes there. So I've got 35 over 100, or 1,000, sorry, times, what is this number here? What's 1 subtract 1 over 100? Don't use your calculator, come on.
0.99.
Yeah, it's a fraction one. 99 over 100, right? If I change this and get a common denominator, that becomes 100 over 100, right? Subtract 1, 99 over 100. So now I'm going to flip it. That becomes 100 over 99. So we're still following through in our book here. Okay. That's going to give me 35 over 990. So far, we're okay?
We should cross those. How do we get 35 over 990?
Well, 100 goes into this 10 times.
Oh, and then 10 times 99.
35 times 1, 10 times 990, or 99. Okay? Let's try and do that in my head here. Okay? So far we're okay. Now, I have 2 plus, so 1 we have to change to a fraction as well. So that's 1/10 plus 35 over 990. So I've got 1/10 plus that, which is going to give me 2 plus, I got a common denominator. What do I times 10 by to get to 990? 99. So that becomes 99 over 990 plus 35 over 990. Which is equal to 2 and 134 over 990. And that is equivalent to 2.135.
Then you just punch 2.125 into your calculator and hit the fraction button.
Did it work out? Did you try it? Or actually, I would do it the other way. I would, on that calculator, I would take 990 times 2, add 134, hit equals, divide by 990, and then hit equals.
Yeah.
Does it give you 2.135 repeat?
Yeah.
Awesome. Okay,
So you can't use the button.
say that again.
You can't punch 2.135 and get the fraction.
Because you can't show a repeated decimal on there,
Oh,
right?
yeah.
It's always gonna have a terminating portion to it. So like if you punched in 2.13535353535, maybe, but I doubt it.
Yeah, because when you do 2.135, it gives you 427 over 200.
Yeah, it's gonna give you, you can't get the repeated portion of it by punching into your calculator hammer. Okay, all right. So this is just simply following steps. All right, let's review then, right here so we know what's going on. Okay, so the question
You
started,
did the same. Sorry.
did it actually give you,
Yes, because you did 1, 2, 3, 3 of them.
yeah,
So I did 3 of them too.
Yeah.
And I got 2.13525. Or I'm sorry, for the fraction I got 1,057 over 495.
which is this reduced?
Then
Okay.
then I divided.
Yeah, okay. So it worked. I didn't know if you could do a repeated part because you had it, so you'd have to go, you did it 3 times, the 135s? Okay. All right, so just to refresh what's happening here. The first thing you do is you isolate your non-repeating part. And then that adds on to this as a repeated decimal. So we just expanded this out to get our common ratio. Once I had my common ratio, so I went from there to there. Once I had my common ratio, then I was using the infinite geometric series equation. All right. And then I changed that to a fraction as well, and I made it all one big fraction here. All right. You see, this is, it's only one question, but that's the only question that you're going to see based on it. Okay. All right. So into 1.5 then today. Yeah.
When you divide them, did you just times them? Like,
I
Once you
multiply
subtract
by the reciprocal of this. This is 35 over 1,000 over 99 over 100. And when you divide fractions, you multiply by the reciprocal of the bottom fraction. So that's what this is. This is reciprocal. And then I just cancel to make the math easier. Okay? All right? Okay. You had a look just for a second there at 1.4. Let me know what, if there's any questions, sorry. Are there any questions on 1.4?